Great. Thank you for the invitation and for the introduction. And also, welcome to everyone from IFML to the assignment workshop. So I'm one of the coordinators for the data-driven decision-making decision processes program this semester. It's great to have you on. Hopefully, you can talk to many of the other semester participants and find out about what we're working on. So I'm going to talk a little bit about, and actually this talk is maybe a bit of an example of what this entire program is about. So I'm going to talk about online decision making, but in particular, a large part of the program, we've been thinking about online decision making and how we come up with algorithms which adapt better to sort of problem instances. So if the problem is simpler, how do we get better bounds and how do we sort of get worst case bounds in general? And I'll talk about one particular technique which I've been sort of looking at over the last 4 or 5 years, this idea of using a coupling, in particular using this idea of the compensated coupling, and I'll try to convince you why, in some sense, in many of these online decision-making problems, thinking about the future is actually the best sense for taking decisions about the present. And my plan for this talk is, instead of telling you what is, my mic's up, sorry. So my plan for this talk is, instead of talking about sort of the best of what we can do with this technique, I'll instead just focus on a very, very simple problem and try to illustrate exactly how this technique works. So I'll actually try to go into a proof and go through it in all its gory details. This is going to be a very simple setting for using this, but the hope is that towards the end of the talk, maybe I'll talk a bit about like how this extends to other settings and kind of point you to some talks next week, which will go into more details. And the simple setting I'm going to talk about is this one. So this is a problem which I have meditated on for like the last 4 or 5 years, and I still keep thinking about it all the time. So it's what I call the online unit demand knapsack. So the idea is, as a principle, you start off with some fixed resource. So maybe you have 3 units of a resource at the beginning, and then you have a set of arriving agents, each of whom has a value. So the tth agent has some value VT, and when the agent comes, you need to either decide to accept the agent, in which case you use up 1 unit of the resource, or you can reject the agent, in which case you don't use up any resource, but you don't get the guy's value. And you can only accept up to B agents, which was your initial budget. So that's sort of the example I want to think about. And the reason I want to think about is I actually think of this as sort of one of the simplest test cases for thinking about online decision making. In some sense, like whenever you have something new which you feel is a better algorithm for some very complicated setting, if it does not do better than what we know here, well, maybe go back and think again. But a lot of insight, like this setting sort of simplifies everything down to the bare bones, and you get a lot of insight from just wondering about it. Now, some of you may think about this setting and say, well, okay, I've not specified where the values come from, but suppose the values came from some known distribution. Well, then this is a really, really simple Markov decision process. It's a one-dimensional Markov decision process. I'm sure most of you, if you try, you'll very quickly be able to actually write out a closed form solution for what is optimal. So it's a little odd that we still think so much about it. But one reason for thinking about it, so if any of you are at this point wanting to give up and say, okay, this is too simple, I don't want to think about this. Well, here's a sort of generalization of this problem, which already brings in a lot of the complexities of general MDP. So what if instead of having 1 resource, I have D different resources with sort of different initial budgets, B1, B2 up to BD. And now each agent still offers me some value VI, but in addition, they also want some subset of resources. So the story, at least in operations research, is you're trying to take a flight from A to B, but there's no direct flight. You have to take a one-hop flight. You need both the tickets in order to buy this. And you again want to allocate these resources while obeying the resource constraints over time in order to try and maximize your revenue. And the problem now is this is a very small extension of the online knapsack, but you already start getting what's called the curse of dimensionality. So in particular, the size of the state space, if you just write this down as an MDP, is something like order T to the D plus 1. And now if you try using your favorite reinforcement learning algorithm, it'll work eventually, but it's going to give some sort of a Baroque solution that will take forever. It's not very interesting. Does this make sense? So I want to think about the simpler problem, but kind of with an eye towards something which looks more complicated like this. And one problem with working with something complicated like this is, well, if I don't even know what the optimal solution looks like, or if the optimal solution is this complicated, how do I even reason about it? And the way that people have been reasoning about it in computer science and operations research for a long time is thinking instead about a benchmark, which is easier to compute. So I want some upper bound for this problem, which may not be the optimal solution, but which is somehow guaranteed to be an upper bound. And here is the simplest upper bound you can think of, which is, well, what if I told you all the arrivals? What would you do? In this case, this is just now, I mean, in the case of the unit demand knapsack, the solution is obvious. You sort all the values and pick the top B. So what I've written over here is that the optimal solution is just the sum of the bth largest value. So the bth largest order statistics of this distribution of the arrivals. But even more generally, even if I gave you the online packing problem, you could still define this object. You can solve an integer program, and that will give you the optimal solution. Right. So the question that we're interested in is, for problems of this sort, can I come up with some kind of nice benchmark for the optimal solution? And then can I try and come up with some nice algorithm which does well compared to this benchmark in an additive sense? So what is the additive loss compared to this benchmark? And this is a problem for the particular case of unit demand knapsack. This has actually been studied for a really long time. So the literature on this goes back all the way back to the 80s. We knew what the optimal solution was, but there was still this beautiful set of work by Hill and Kurtz and also Esther Samuel Carvin. They thought about this problem for just a single item. So it's sort of the simplest setting of this, but came up with really like much simpler algorithms than the optimal, which was still within a constant factor of the optimal. So they got a constant factor of whatever the optimal MDP solution was getting. And these ideas have been generalized extensively by the TCS community in like the last 10 to 12 years. To a very wide variety of settings. And actually, we have a lot of people in the program who are experts on thinking about these processes on matroids, on all sorts of sort of complicated constraint sets, and trying to come up with these kind of constant factor algorithms. This is amazing. However, there is a problem that all of this works extremely well if you have a small number of items. As you increase the number of items, like getting a constant factor basically means your regret is scaling with the number of items. So if your number of items is on the order of the horizon, that's not great. You don't want to lose half your revenue if you're selling a lot of things. There are better answers for this. I mean, you can show the competitive ratio slightly better than this, but morally, the regret is still scaling with the parameters of the problem. Now, there's a different line of work coming more from the operations research and the applied probability domains, where what people have been thinking of is, instead of having these kind of completely arbitrary like distributions, you fix the arrival process and make the arrival process independent of the horizon. So one simple example of this is, well, what if you had IID arrivals from some known distribution? And you still want to ask this question about, okay, how well can you solve the online packing problem compared to the offline optimal? And there we've again, this has also been studied for like nigh on 30 years. And we essentially know that in a regime like this, the regret you can get is something like square root t. Now, why square root t should make sense is, well, if you just think about the setting without the constraints, this is the uncertainty just coming from the central limit theorem on what these values are. And what these results are effectively saying is you can always get a regret on the order of the central limit theorem. You can actually do better than that. So this was an amazing result by Marty Ryman and Cheung Wang back in 2008, where they proved that there should be an algorithm which does strictly better than square root t, and in some, but we couldn't kind of figure out exactly what that should be in, or there wasn't a clean way to understand it. Later on, Jason and Kumar showed that there were ways of, like, if you kind of removed some subset of inputs, so under a certain condition called dual non-degeneracy, you could get a constant regret, a regret which didn't even depend on the parameters, but as you went closer to these sort of degenerate instances, you again went back to square root t. And this is sort of where things were back in like 2015 or so. So this is sort of where I started thinking of this problem, and kind of the strange question I wanted to think about was, well, what if you fix this arrival process? So for example, what if I say that I have a finite set of values and each value vi arrives with some probability pi IID, and these pi's have nothing to do with t. These are just numbers given to you. And now I scale both T and B. So I make the problem bigger and bigger in terms of the state space. I have larger horizons, I have larger budgets, but I'm freezing the remaining parameters of the problem. I'm not sort of taking this dual limit. So what is the best regret you can get in a domain like this? And surprisingly, the answer is that, at least for the online knapsack, under any arrival process over a finite type space, there is a very simple algorithm which actually has regret, which is a constant. It does not scale at all with the budget or the time horizon. In fact, you can give very simple expressions for an upper bound on the regret. This is far from being tight, but what it's saying is, okay, it depends on the maximum value. It depends on these IID probabilities, which are fixed up front. Of course, if you change the probabilities or if you make them dependent on T, this bound it's not as strong. But once you fix everything, your regret is at most this. It has nothing to do with the budget or the time process. So something interesting is happening in these problems, which is making them much easier than what we believed was true. And pretty much since then, so okay, firstly, some of you may think this is just theory, but no, this is actually true in practice. So these algorithms are incredibly useful. Like if you try just using them compared to what existed in the state of the art, what I'm doing here is I'm taking, this is an online packing problem in higher dimensions. I'm basically now scaling the budget and I'm scaling the time horizon and looking at the regret. So these were sort of the state of the art algorithms that we knew. This is roughly a square root T regret. This is what we get. There's just no sort of tricks going on over here. There's a small change in the algorithm, which kind of immediately collapses the regret all the way down here. And most of what we've been thinking about since then, at least in the OR community, has been sort of taking this as a primitive and then thinking about, okay, how far can you push it? How far can you push these assumptions? What else can you do, etc. So my aim today is going to be to try and talk a little bit about how we get this and what are the techniques which led to it. But I just wanted to show all of this to motivate you all in case, like, I'm going to go deep into the weeds of the maths after this, but just want to make sure everyone's somewhat interested in the weeds. So any questions at this point?
So yeah. Time is the V over T like a constant?
No, no, they could actually scale in completely arbitrary ways. So there was an intermediate result when the budget over time is a constant, when actually there was a parallel result to us which showed that in that regime something else was doing well, but actually none of that matters. The budget and the time can scale any way they want. Okay, so I'm hoping I've got you all sufficiently interested to spend the next 20 minutes getting into the weeds of this. And so what I want to talk to you about is, as promised, the compensated coupling, which is essentially a different way of thinking about these problems, which leads to these results. And several of you have seen this before, or okay, so some of you have seen this before, but for everyone else, this is the main idea. This is kind of the high-level idea of what's going on in the coupling. So the idea is that you have two controllers. And think of this as an online controller, which is the algorithm that's going ahead and taking certain actions. And then you have some sort of offline controller, which knows the entire history. So which knows exactly what's coming in the future and is taking decisions based on this information. So what I want to do in regret is I want to compare how well the online controller does with the offline. The important thing about this offline controller is because it knows the future, I can sort of throw the offline controller in some bizarre state in the middle. Like you can think of one of these like choose your own mystery kind of books where you go into the middle and then you are in some strange state and the offline still knows what's the right thing to do in order to reach the future because it knows the future. And I want to know how to compare the two. And here's the idea of creating the coupling. So I'm going to follow a single sample path. So I'll run one simulation of this problem and I'll follow these two algorithms until the first time when one of these algorithms, in particular, the offline algorithm wants to do something different from the online algorithm. So this is the first time when these two are separating out. And what I'll do at this instance is I'm going to force the offline algorithm to give up on what it wanted to do and instead follow the online algorithm. Now, of course, the offline algorithm isn't happy at this process because it knows that by taking this action, it's going to lose out in the future on this sample path. But I'm somehow going to try and figure out a random variable which would compensate the offline for taking this action at this point. So this is going to be the main idea. So let me actually formalize this a bit. So here is the same thing in a little more gory math. So what I really mean by an online and an offline controller is I have two different algorithms which have different data available to it. So when I say a richer filtration and a natural filtration, that is probabilist speak for saying what is the data available to the algorithm when it's making its decision. So the natural filtration is whatever data you've seen up to now, the history of the process. A richer filtration is something which has extra data about the future in order to make its decisions. And at any time, now given these data sets, I can define the value that, like at any time and any state, I can define the value that the online algorithm and the offline algorithm will get if I start at that state at that time. So for the online algorithm, this is exactly a value function. This is the value, the expected value if you follow this policy from now onto the future. For the offline, it's something a little more complicated. So in the case where GT is like the full data set, if you know all future values, this would exactly be the sort of ex post value of the optimal solution starting from that state. Does this make sense what these objects are? But these are both random variables because they sort of depend on the sample path and the filtrations. And now here's kind of the way to formalize what I said in the previous slide. So I'm following the online algorithm. So everything in green is as seen by an online algorithm. And I reach a certain state. And at this state, offline and online are taking different actions and they're going to different points. So what I want to do is I want to somehow force the offline guy to not take this orange action, but instead take the green action. And I need to compensate the offline for this process. So formally, what this means is the offline is thinking about getting its value function from this state onward. And instead of allowing it to do so, I will force it to take the action that online is taking, at which point it's going to get some instantaneous reward. It's going to transition exactly the same way as the online algorithm transition. So get the value function of the next state of the online algorithm. And then there's some random variable in between, which would sort of compensate the left-hand side and the right-hand side. Like the left-hand side should be bigger than the right-hand side, but I'm adding this blue delta in order to make sure that it's not. Why is this nice? Well, I can keep, oh yeah, go ahead.
I have a question.
Excellent.
So, like, why do you need the past in the offline? If you know a state, and if you know the future, you don't need the past.
Yeah, I don't need the past. I mean, in more complicated settings, I may need the past.
But you don't want this richer filtration.
No, but the richer filtration just means I know everything online knows plus the future. There are examples where you need the past, but in this one, yeah, we can. But it's not without loss of generality. Right? Like, I can have extra data. It's a fair question. Okay, but at this point, what I'm now going to do is when I have an equation of this sort, I can just telescope it. So I can just follow online along the sample path. And if I telescope it, what you're going to get is something like the following. So as the V offline on both sides keep canceling out until all you're left with is V offline in the initial time. And the sum of all the rewards, which is exactly what the online got on the sample path. And the difference of the two is the summation of all these compensations. So the difference of the two, by definition, is the regret of this process.
So is delta the smallest number?
No, any number which is guaranteed to be greater or more. Yeah. Does this make sense? Okay, good. So if this seemed too weird and unfamiliar, at least for any of you who have seen reinforcement learning, you would have seen some version of this before. So if you've ever seen the performance difference lemma of Kakade and Langford, that's a special case of the compensated coupling, where you think about both the policies as having the same filtration. So if both the policies are adapted to the sort of natural filtration, then when you add this up, what you basically get is you're looking at the value function of some policy pi hat with respect to the sample paths taken by policy pi, which exactly works out to be the sort of sample path average of what's called the advantage function of this policy. This didn't make sense, not very important, but it just so turns out that, like, at least in reinforcement learning, this is kind of one of the workhorse things that you use for most of the analysis. For any of you who came to Kevin and Andrew's talk on Wednesday, they were sort of using this and doing kind of amazing things with it. But this is just a natural conclusion of this coupling if you just feed in the natural filtration. But I'm kind of insisting on using a richer filtration. So why am I doing that? What do we get if I use the richer filtration? And this is going to get me back to the question about the online unit demand knapsack. So what I now want to show you in the remaining 10 minutes or so is how can we, like, I've set up this coupling. This is a general way of giving us bounds for any online decision-making process, but the ability to somehow peek into the future actually gives us much stronger bounds in certain cases. I will try to illustrate this very literally. So remember, this was my online unit demand knapsack, and what I'm now assuming is that the value at each time is drawn from some known CDF capital F. It's drawn from some known distribution, and I still want to maximize the sum of the rewards. And for the moment, just for simplicity, let's even assume that the CDF is the uniform on 0, 1. So I'm drawing values from uniform 0, 1, and I want to try and maximize the reward. And I've sort of plonked you down on this problem somewhere in the middle, where I have h plus 1 time steps left, and I have some budget small b. Something has happened in the future, forget about the future, doesn't matter. Now, what's going to happen at this point is if I go and ask offline, hey, what's the largest, like, what's the sort of your value from now till the future? He's going to say, well, I'm going to pick the b largest arrivals in the remaining h in the future. And I'm going to call this quantity v of the b at largest, I'll call it v of h minus b, and that's some point between 0 and 1. Now, I don't know this. I don't know what's coming in the future. I need to decide what to do with the current arrival. So what I'm going to do is I'll choose some point theta, and if the current arrival is bigger than that, I'll accept it, else I'll reject it. Now, if you think a bit about what the offline guy is doing, this was the bth largest thing in the future. If the current arrival was bigger than this, he would have accepted it. If it was smaller than this, he would have rejected it. So what this really means is in these two regions on either side, we actually have no compensation. We both completely agree. The offline agent with extra information and me as an online agent without knowing the future know exactly what the right value is. So some of the only uncertainty is happening in this little region in between my threshold and VH minus B. And you can sort of reverse the same thing and say, okay, what if theta was bigger? And you'll get almost a similar picture. Okay. And at this point, I can actually directly calculate the compensation, because if the current arrival is some value over here and I accept it, then I need to give up on this value in the future. And so my compensation is exactly the difference of the two. And you can kind of, again, think about this thing when theta and v are reversed, and you'll get something very similar. So sort of this is my compensation conditioned on knowing the future value and without knowing the current value, or if the current value is v. And if I average over the current value, so if I average over vt, I'm basically paying the length of this distance under just the Lebesgue measure, since I have a uniform distribution, which is basically this VHB minus theta the whole square, basically the square of this interval. This is just simple geometry. So I somehow need to be able to understand this. Like, all of this is conditioned on knowing the h minus b of the future. For the uniform, you can now kind of simply just solve this because we know everything about order statistics, but how do I do it for a general distribution? And what even is the right policy for a general distribution? So here's the policy that I had proposed with Alberto back in like 2018 now. So this is what we call the base selector. And the idea was that, well, suppose I knew the CDF at some time t, if I have at small time small t, if this is the time to go, let me look at my normalized budget. So budget divided by the remaining time. So project that onto the CDF and then look at what the threshold is. That's a sort of natural boundary to decide whether to accept or reject. If my current value is higher than that, I accept, otherwise I reject. There's sort of a small but really, really important tie-breaking issue. So what happens if my boundary falls in between? The right thing to do is then to actually snap to the closer point. So you sort of divide it right in between and then decide, so here the threshold is V, here the threshold is sort of V minus. This is surprisingly critical, but we know what to do. Okay, so that's my threshold. How do I analyze it? How do I figure out the compensation? Well, here is the idea. So in order to figure out the compensation, suppose I told you what the future samples were. So in orange, I'm drawing out what all the future samples were from now till the end of time. And one thing you can clearly see from this is if you just draw out the empirical CDF with like height 1 over t minus t, you'll kind of see that in future, I would have been accepting this, this, and this sample. These are the three things which would have fit into my budget, just by drawing the CDF and extending out the remaining budget. So the only place, again, that I'm making a mistake is in this little region here. If my current arrival falls in this little region over here, I make a mistake. Anywhere else, I don't actually pay a compensation compared to the future. It's exactly the same as what I did with the uniform, but now just looking at the general geometry of these processes. Okay, so I somehow need to understand how to bound the probability of falling in between, or the square of this distance. But that's usually a tricky thing to do. I mean, it's very hard to think about what's the probability of falling in this region under a general distribution. However, I can project it onto the y-axis and instead think about gaps between my CDFs. Now you may think, okay, it's not totally clear why that's easier, but as long as this curve is it's Lipschitz, I can convert distances on the x-axis to distances on the y-axis and sort of look at the CDF. And now here is the same compensation argument as before. So I'm again trying to integrate the probability of falling in or the length of this region under now this distribution small f. Suppose this distribution was upper bounded by some capital M. Well, I can just bound this by m times the square of the length. This was exactly what I had done before. I don't know how to analyze the square of this distance for some general distribution, but as long as the distribution is anti-concentrated, so if it's bounded below by some small m, well, it's at most the sort of worst case length or the worst case distance between the empirical CDF and the true CDF. If this didn't make sense, it's just algebra. There's nothing fancy going on. All I've said is I can write down the compensation that I pay at each time, at least for well-behaved random variables, in terms of the distance between some empirical CDF and some true CDF. And everything up to now has been elementary in some sense. And this is the only time when you'll need a slightly heavier hammer, but anyone of you who does like online learning or applied probability will kind of know that this object is actually extremely well behaved. So the empirical CDF and the true CDF for any distribution is uniformly bounded, or it's uniformly concentrated. The result, which is often called the DKW, the Dvoretsky-Kiefer-Wolfowitz inequality, the sort of particular numerical form is due to Massart. And at this point, I'm done. Like all the calculations I've done before just for the uniform distribution, I can just port it over because I know how to analyze the difference between my CDFs. And basically, if you just do a little bit of algebra now, you'll get this is essentially 1 over t minus t. When you add it up, you get a log t regret. So just an elementary coupling plus this one non-trivial uniform concentration bound allows you to show that for any distribution here, which is at least anti-concentrated, you should get a log t regret. And actually, you can kind of see why you can use this to analyze anything else. So as an example, if your distribution wasn't even bounded, or if it wasn't even on a compact set, but let's say it's sub-exponential or it's monotone hazard rate, you can kind of churn through the same machinery and you will get other constants that show up and you'll still get log t regret in each of these cases. 2 minutes? Questions?
You said n is the number of heads.
Small m? No, the small m here? Oh, n, yes, over here. This is the number of arrivals in the future. So it's the number of things you're using to compute the CDF, the empirical CDF. So the empirical CDF is drawn using 8 samples in the future. So let me show you one last little magic trick. So, okay, something algebra. Why is this useful? Here's another thing you could have asked, which is, well, what if the f was unknown? Sure, many of you think about, or at least must have been thinking about it. You assume the f is known. Well, what if it's just IID? And the natural thing to do would be, well, do the same thing, just use the plugin estimator. So just take the t samples up till now, look at their empirical CDF, do exactly the same thing that I described. And well, how well does this do? But instead of asking how much does this lose compared to offline, I can sort of, because the compensations are, they're sort of composable, I can instead compare against the algorithm that I already analyzed online with the known CDF. I already know this is log t away from the offline. So if I could prove this is also log t away from this empirical version of the algorithm, I would have got a 2 log t bound. But I claim this is immediate because actually it's the same problem in reverse. So what did we earlier analyze? We sort of looked at a known CDF and an empirical distribution, but that's actually exactly what I'm looking at now. Nothing has changed. It's just like looking backward versus looking forward. It's the same analysis. You can again do the same. In fact, you can do an even more general statement, which is, well, whatever analysis you had for the forward regret, if you use the plugin estimator, you just get twice of that for the backward, for the unknown distribution. So kind of what's more powerful about this technique is, well, firstly, it lets you do this more detailed calculation, but it also sort of just naturally extends to other things which you may want to do. So in the last 20 seconds, I hope I've got you all somewhat interested in this technique. And you may be thinking, okay, does this go beyond just the online unit demand knapsack, or have we wasted half an hour just thinking about this one very simple problem? Well, luckily it goes far beyond. So as an example, you may be interested in something like online vector bin packing, a much harder problem, one which we had very little idea of what to do beyond a square root t regret. But in work with Daniel Freund, we showed that if you just look at online vector bin packing with sort of arrivals under mild assumptions, you again get an algorithm which has constant loss compared to the offline. And this is in log plot. What I'm showing are existing algorithms which have some polynomial loss, and here is effectively constant loss modulo with some noise. You can do.
Are you fixing the number of bins as constant?
No. So I'm saying jobs are coming in. I can create bins. I want to minimize the number of bins I use to pack these jobs into the bins. So this problem, yeah, I mean, even the offline problem is NP hard. But if you scale T, it's not, and then this becomes, you get a constant regret. You can sort of extend it to other bizarre things like doing online pricing. If any of you are interested in dynamic pricing, you also have constant regret algorithms for dynamic pricing. I'm not going to say much more because luckily for me, this gentleman in between is going to actually give a much longer talk on these more advanced things. So please look out for this on Monday, and I will stop. Thank you.
Thank you. And so we'll reconvene in 8 minutes. Thank you. I'm gonna go back.